Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is the AAS Journal Author Series. And I'm very happy to have Sara Faggi with us today. Hey, Sara.
Hi. Hi, nice to meet you, and hi, everybody. Thank you for inviting me.
Well, thank you for agreeing to talk about your really lovely article. It's
really my pleasure.
And Sara, where are you located at?
So I am in Washington, D.C., but precisely Bethesda, Maryland, close to Washington, D.C. And I'm here because I am a NASA Goddard. And so that was the place that I choose for living.
Nice.
And I'm also a professor at American University in Washington, D.C. So it was like a middle point, good middle point to live.
Very good. Very good. And I see we have a visitor over your left shoulder.
Yeah, she decided to show herself. Hi, over there.
What's the name?
Oh, she's Mina. She's yes. she's our little helper for astronomy.
Cat-eye nebula. Very cool. All black too. That's some pretty cool artwork over your shoulder. Did you do that artwork?
Yes, actually, there are small stones coming from a beach in Italy, which are actually not really stone. They're tiles that the sea like sort of shaped. They're all brick tiles in that beach, and the sea like shaped them, and so we just collect them, and I just decided to do something on that.
They're beautiful. Oh, those are awesome. Those are awesome. You should get into a sideline of selling some of those on PayPal or something along those lines. Something
like that, right? Yeah, I thought about just, enjoy them, remind me of my country.
There you go. Whereabouts in Italy?
Oh, I'm from Florence.
Florence, okay.
Yes, in the middle, the heart, I would say.
The heart.
Very unbiased opinion.
Oh, we take biased opinions. It's okay, especially when it comes to Italy. So very cool, very nice. And Sara, what do you like to do for research?
So I am a spectroscopy, basically, molecular spectroscopy. So I study the composition of comets, and recently I started to study also atmosphere composition, mostly Mars. But I've been doing my research mainly on comets so far. So I've been studying with ground-based high-resolution spectrometer, like JANO at TNG in Canary Island, or iShell IRTF, or the nearest Keck-2. So I've been observing comets from the ground. So I'm an astronomer, spectroscopist, and what I do is understanding their composition. And yes, and basically we are interested mostly in the 2.5 to 5 micron region, because that's what we call the molecular machine, in a sort of way that's where we can capture all the organics and the molecular feature there. So yeah, that's why it's interesting.
Cool. And that is going to bring us to this very lovely AJ article, The Extraordinary Passage of Comet C2020F3 NEOWISE, Evidence for Heterogeneous Chemical Inventory in its Nucleus. And Sara, take us away.
Thank you. Yeah, so first of all, I want to thank all the other co-authors that worked with me on this paper. Manuela, of course, that she's been also my office mate for 4 years. And then Maria, that she was in NASA, and now she's in Caltech. Camillus, Geronimo, Greg, that performed the observation and was very helpful. Jeff and Mike. So thanks for everybody, to all of them for the help. Yeah. So in this work, we observed Comet NEOWISE. Comet NEOWISE was observed last year in July and August 2020 in the middle of the pandemic, and we did observation in what we say the pajama mode, so at home, observing remotely. And these observations are part of the DTT time, so what we call the direct discretionary time that we ask to the NASA IRTF facility. And then we follow up, with Keck Observatory. So this comet brightened up so much. It was discovered in March, if I remember correctly, and then it started brightening up, and it was spectacular. And it was one of the brightest comets of the century, after probably the Hale-Bopp and the Hyakutake. So it was like we had to observe it. And so of course. So we asked for directory discretionary time, and we actually won a couple of, like 6 nights or something like that.
Nice.
And then we start observing the comet on the 13th. We can actually go to figure 1, where actually there are the different dates and the observation and how we follow the comets.
Okay.
And yeah, we can see there the dates that we were awarded and how we follow the comet. So yes, we had these first 4 nights with the IRTF.
Okay.
And we used the iShell spectrograph, which I'm gonna say a little bit more about it.
Mm-hmm.
And then we continue observing with Keck a couple of nights. Cool. So yeah, so the comet was, as you can see in the table 1, that is the log information of the object. The comet was spanning a different heliocentric distances, but very, very close, because there was from 0.34 to 0.8 astronomical unit. It was inbound, it was after perihelion, and it was also very close because it was a 0.9, between 0.9 and 0.8 astronomical unit in delta. So it was not that far from us. Yep. And another important parameter is the delta dot, so the velocity relative to observer. And as you can see, it was minus 59 and plus 33, so very high number though. It means that that was a key thing. That's why we asked DDT time also on this object, because we could shift the cometary lines from the telluric counterpart. Okay. That otherwise would absorb them. And so especially for methane and CO, we were able to study those two. So we got lucky that in those dates, we had a very high Doppler shift, and we could investigate those emission lines. Nice. So we followed the comet on the 9th, almost for 1 month, but from the 9th of July, as you can see here, until the 6th of August in different nights. Yep. And yeah, and this is the observed log. So where everything that we did is basically there. So we followed the comet, and we had a calibration star. And basically we have been following the comet in different settings of ice shell. The setting L1, where we basically target water mainly, and then the nitrate regions, so HCN and ammonia, for example. Okay. And then we decided to move to the LP1 setting, where we can sample ethane, methane, and methanol mostly. Cool. And also we start on one of the other dates, I think it was mostly the 20th and the 31st of July. We pushed a lot in LP1 for HDO, because the comet was very active. And so we tried to get an HDO measurement, which is not reported in this paper, because we had so many interesting topics on this object. It was so active that this paper is just about the molecular composition and what we learned about it, from the spatial profile, from the production rates and everything. But we have many others important information, and so they're gonna come out many other papers. And one of these is the D/H study on this object. It was very interesting. Right. Okay. That was possible in the LP1 setting. And then, as you can see, we also observe in the M band, M1 specifically, where we target CO mostly, and also water close to 4.5 micron. Mm-hmm. So that's overall all the observation that we get. If you scroll down, we can see a little bit of more information, probably also about the instrument. So we observe with iShell and NIRSpec. Probably people that use them knows what they are, but in general, they are high resolution spectrometers. So we work around 70,000 resolving power with iShell and 25,000 with NIRSpec. And as you can see, we have high resolution spectra. And these two instruments work basically at different settings. As I said, iShell, the L1, the LP1, and M1, there are settings that are covering specific wavelength range, and so we can study molecules that are emitting in those wavelength range. But the beauty of those is that you can get them all simultaneously. Yeah. So the water measurement is together done with the organic measurement. So you are actually in some way avoiding some systematics that sometimes happen when getting, information from different instrument or changing the way you observe things, right? So yeah, when you get together simultaneously, you actually are achieving some more reliable information. And so we could observe a lot of water lines, and this is an example. So here I'm putting together from the Sentinel-1, which there are 15 orders. I'm putting together like almost 10, how many they are? Like, 8 orders altogether from 184 that you can see in gray down there, to 172. So those are all spectral order of ice shell, of the shellogram. And basically we're putting them all together and we can get a full simultaneous water measurement.
Nice.
Yeah, and so you can see there an example of the water spectrum. We actually had some unidentified line over there. We can see, for example, the CO spectrum over different order. These are just 4 orders, but you can see how the fluorescence model works nicely. When you put them all together, you can get a more reliable results. And down there, you can see the methanol and the OH from the emission. So that is just an example. Then the other figures show other spectra that we extracted. This is just to show what actually this kind of instrument can provide. So if you scroll down to the other figure, which I think is still figure 2A and 2B.
One question, what are the purple arrows highlighting?
Those were highlighting unidentified lines that were not present, unidentified lines, they were not present in our one fluorescence model. So they, for example, in the third bottom plot, there might be OH prompt emission line that were not present in our model because we use a line list there. We actually don't have a model for that. We use a line list to identify the OH prompt emission. So that might be something, but if you go to the other chart, there are unidentified line also over there, close to the nitrile region. So as you can see, for example, in the fourth chart on the right of the top, there are interesting fissures missing. There might still be OH because it's all over in that range.
I see now.
It is interesting. Or there was an idea there might be ammonia prompt emission because that's wavelength range, but we don't have the line list or the model for those. So we just highlight them and we collect them, and future investigation, people can find them and track the information down, right?
or for analysis later, right?
Exactly. So that's how basically things are. So we start from a spectra, as in the other panel on the left, the first panel on the left.
Let's slide over there.
Where we have actually all the telluric absorption feature of our own atmosphere on the first row spectra that we extract. And basically we have to subtract these telluric features. So we have a model and we implement that with the planetary spectrum generator, which is an online tool, and I can share the link somehow. I think there is somewhere, maybe in the caption. We can show them later.
Yeah, we'll also put that link maybe in the
definitely. And so we basically use the planetary spectrum generator and the MERA, which is a atmospheric climatological repository of NASA, where basically we can have the vertical temperature and information and the abundances of all the molecules of our own atmosphere anywhere in our planet. So we select Mauna Kea, we have the perfect information of above our observations, and we can reconstruct the telluric features like that. So we can then subtract that and we obtain what we call the molecular residual, where we do our fluorescence analysis and our fitting, which is what actually is shown down there, and all in the other plots. I just show one because you lose the emission line there. No, they are not so evident when you have all these huge telluric features. So I just show in one panel, and then in the other one I just show the subtracted molecular residual where we do the modeling. Yes.
For example.
So those, yeah, for example, those is the ice shell one, and the other two bottom one is keck.
Okay.
Same, you can see actually that these are different dates because this is already August 4 and August 6, while the previous one were July 9. So you can see how the dust changed already. The continuum is already completely different because the telluric is the continuum is very high up in the 9 of July. The comet was closer to the sun. Yeah, and you see how the continuum already is more faint.
Yep.
So also the telluric fitting is easier, I would say, because that's affect all the baseline and all the, subtraction affects all your molecular residual. So yeah, that's basically sort of spectra that we extract and then we work on. Nice. And yeah, and in this comet, we immediately saw something interesting as soon as we observe it. And that's actually, I report this, and it's an example of the shellogram and the nodding technique that we use. And is, I think, in the next figure, if I recall correctly. It's a long paper. Sometimes I forget which figure is the number.
Oh, trust me, I understand. I understand.
Yes, I have in my mind actually what I want to talk about. But so I think it's the next figure. Yes, here we go. So in this panel, we have an image of the IRTF guider. And these were daytime observations. So it's already showing how powerful is the IRTF guider for ice shell. Like we can allow us to observe comets daytime. Nice. Yes, it's very powerful. So basically we do this that we call ABBA nodded technique. Okay. And yes, and this will allow us basically to correct for sky subtraction because it's very important, especially for daytime observations. Yeah. And so what we get from that when we do the A minus the B beams is what you can see here in the right panel here together close to the imagery. Yes, so basically we have the A beam in white and the B beam is that strips in black. So each of those strips are one spectral order. And when we do the subtraction I minus B of all the beam and stack them all together, we can appreciate that the information is the same. It's just one is in positive and the other one is in the negative, basically. And what we do then, we extract, we straighten the order, we clean them from the pixel, we do all the calibration, frequency calibration, which I'm not going into details, but we do all the work. We combine them together, and in that way we have a full clean bin where we work and we extract our spectra. So, but just to see that we already learned something from the shallogram when we observe this comet, which is not usually what we can do because you have to extract the spectra to see actually what you have, right? Sometimes the lines are not so obvious. Yeah, but as you can see here, they were incredibly intense, and you might appreciate also that the continuum, which is that line, the horizontal line at each frequency, it's not completely overimposed to the center of the peak of the line. So you can see, for example, that the line extends to the end of the end of the beam there of the order, and the peak is not perfectly aligned to the continuum peak. It's not easy to see there, but maybe in the not the last one, in the previous one, you can see in how the A beam is a little bit shifted. So that you could already see in the shallogram. Yeah. Also in the second one from the bottom, from the top, sorry, you can see how the first line over there, the peak is not centered on the continuum. Yeah. So that was already, whoa, what is going on there? It's interesting, right? Yeah. What was going on is actually the plot that is above, that chart with all those lines, which are actually no lines. Those are spatial profiles. So it is, yes, it is the profile of specific lines. So water, HCN, ethane, all the molecules that we observe, we extract the profile along the slit, which gives us give us information about the spatial profile of the molecule, right, themselves, so the spatial information. So, okay, so the gray shades are where the slit, the combination of the two beam between the A and the B beam, like when they overlap, we have the middle region where we have the lines, the profiles, and the gray shade is where we do not consider those. Okay. So, yeah, so at the beginning, you can see in the 9th of July where the comet was very close by, and we were it was very close. So when we were combining them, since they were shifted, and we're going to talk about that, the region that we could actually investigate those profiles is very narrow, unfortunately. And then later on, it becomes more wide. And yeah, and you can see, for example, if we pick the 20th of July, just because it's the only date where we had them all the molecules, we could then, you can see how the gas peak is shifted from the dust peak. And that is the extraction of the profile of the line, emission line, along the slit, and the extraction of the profile of the dust close by. Okay. So where there is no emission line. And we see them, they are, and then when we recenter to the dust one, because we assume that the nucleus is there, right? And it's in some way, that's where your dust also profiles should start, no? Yes. We see that the gas was shifted in the anti-sunward direction. And that was already, whoa, this is huge shift. This is a huge shift. Yeah. Interesting. Yeah, it's interesting. And that was for all the molecule, except for NH2, which is a daughter species. It's not a primary molecule. And what we do usually is study primary molecules. Okay. So, water, HCN, ammonia, and so on and so forth. But NH2 was very bright, and we had it there. So we don't have a fluorescence model for that, but we do we can study the spatial profile. And we saw that the NH2 was partially extended towards the anti-sunward direction as water or as HCN, but also was following the dust. So it was broader, which is expected from a daughter species, right? It's broader. Yeah. But that also might be an hint of two possible or multiple possible progenitor, not just a progenitor in the gas phase, but something that might be in the refractory, so in the dust phase. Yeah. So that was something that was really interesting. It was clearly a qualitatively judgment of that, because we couldn't really demonstrate quantitatively, but that was something really interesting. It was pointing out there was not just one progenitor, so it was interesting. Yeah, and then interestingly, after the 20th of July, that shift disappeared. Yeah. Yeah, so what happened there, right? I don't know. Well, okay, so we'll see what happened there. We'll see what happened there. I'll say I'll reveal at the end of the movie who was the killer. No, I'm just kidding. So yeah, so let's keep in mind that we have this shift. Yes. And this shift, we interpret them as possible icy grain or nearly pure water icy grain that were in some way released. They can be an outburst, they can be a jet that was releasing material. Yes, right. Yeah, and so those icy grain in some way were sublimating at that distances, and they were creating this peak of emission there. So it was not centered on the nucleus, basically. That was one of the interpretations, yes. So if what we do actually is quantification of the production rates. So what we do, if you can go down, is from this line that were either centered or not centered from the dust. Or this is another thing that that we actually investigated. We can actually spend one word about it, but yeah. So basically, we also studied the dust profile, how they were in the different settings, and interestingly, the dust was enhanced in some way in the sunward directions on the other side, right? So they were all peaked in the same position, right?
Yep.
but the extension, like the slope, was different between the different settings, so between wavelengths, we can say.
Yes.
And so we interpret that just simply like physics. So close to L band, you have thermal emission and scattering of the sunlight, while in M band, you are dominated by the thermal. So the slope is just steeper because of that. Okay. So that can be a reason. So there might be some dust release in the sunward facing side of the comet, and that's simply, the profile might be simply physics explanation. And yeah, and so we also compared some of them with the molecules, and so actually what was following what. But to go back to what we actually are quantifying, right. which is why it's interesting to put them all together with the spatial profile investigation. What we investigate is the production rate. So how much water we have and how much of other, yeah, you can show that table. I can show maybe there are some numbers. And all the table are reporting all the quantitative information that I talk about. Even for the spatial profile, we are showing there, for example, all the summary of the spatial profile information. So the analysis of these profiles. So where the shift were, which is the Q scale that we perform from there, which is I'm gonna explain what it is in a second. But just to say that each table, it's just gonna provide in the numbers of what I'm talking about. Mm-hmm. Yeah. So yeah, if we can go down, we have information about the molecule. So yeah, the production rate and then the mixing ratios. So here we go. So basically, what we do. Yeah, basically what we do is we perform both correlation and Boltzmann analysis. They're two similar and different though approach. And okay. what we extract is the rotational temperature, which is basically the temperature of the ground state of the Boltzmann distribution of the ground state before these molecules get excited and then they will re-emit. So basically, that's the temperature that we are extracting. Got it. And we have these two techniques. One is for the correlation. So we correlate the fluorescence model with the spectra observed, and we extract these parameters. And the other one is the Boltzmann analysis of the slope analysis, basically. So what we compare there is line by line, and there is a chart. I reported this technique for, I don't remember, maybe 6 molecules or some of them. I think it's next figure or one of those. There we go. Yeah, there is a figure with all these colored points. Mm-hmm. And point, here we go. Yes, this is the rotational analysis, basically. So for each line, we compare. Basically, for each energy, you can see here in the x-axis is the energy of the Boltzmann distribution of the line. Yeah, and then you have in the y-axis basically the production rate. So you compare when all these lines together will provide a slope 0, which means 1 temperature. Right. When you put them all together, compare, of course, the line with the fluorescence model, with the G factors. Mm-hmm. And basically, we find the best temperature with these two approaches, and then we compare if they are consistent, and usually they are. And when we cannot retrieve a rotational temperature just because we have maybe like 2 lines, or because it's very noisy or it's difficult, we fix 1 temperature, which is usually the most accurate one, for the specific spectral order or spectral setting. We don't apply the same temperature to other dates or other settings. No, has to be usually also the same spectral order, just to be sure that we're doing things right. Okay. And we recover in the way the production rate. And since we have slit losses, we can correct for that. And from this production rate that I just described now, which is extracted from the center pixel of the line. So we have the line shape, no? Along the slit, the profile that I showed you earlier, no? So we extract the first maximum pixel few pixels, we know that we extract sort of based on the slit width, based on other factors, which I'm not going to go into details, but we extract those center pixel, we extract the center production rate there.
Yes, okay.
With the technique that I described now. And then we have to correct for slit losses because we have the seam, right? So we're losing flux. And so the profile analysis will help us in that. So we will compute this production rate along the profile, spatial profile, and then we will find the terminal production rate, and we will find this ratio that is the Q scale between the terminal and the center. And we recorrect our centered values to have a full global production rate for that molecule.
Good.
So it's convoluted, but
I'm with you. Good. I'm with you.
Yeah, it's necessary for this kind of observation. And so this is just an example. So this is all process to finally get to the production rate and to finally get to the mixing ratio, which is the molecular abundances, right? So how much of this molecule I have relative to a baseline, which usually is water, right? Because so historically has been always the baseline for this kind of studies. And so water, though, behave in a very peculiar way in this comet. And as you can see in this plot in figure 5, water was higher in these days before like 9 July and 20 July. We didn't have a measurement for the 14, but we used the OH prompt emission to get information about it.
Okay.
And so these 2 dates are higher in values, while the other dates, it's a bit lower. And so think about that also, the profile of water had those big shifts.
Yes.
While the shift disappeared after the 20, this is already another indication that there was an excess of production rate of water that was not just coming from the nucleus, but it was coming from these ices, from these grains that were released in the coma.
Okay, yes.
And so we try to understand and quantify this. And so that was an exercise that we did, trying to compare this production rate, assuming that the production rate for the nucleus was always the same, it was not changing.
Okay.
And then only in those 2 dates, we had this additional extended source. And so we quantified that actually the extended source was actually almost 50%, if not 60%. It was big. It was a lot of releasing of material from this comet. So there was maybe an outburst, as I said, or maybe it was this kind of jets, spiral jets. We cannot disentangle from this kind of investigation. It would be beautiful to have also, imaging an investigation of those in the same nights to understand what was going on. But that's life, right? So we can't have everything. So yeah, in the next actually plot, I think there is the comparison of these 2 spatial profiles that we had. One was on the 20 and the other one was on the 30 of July. We didn't normalize here. This is just ADU. And so you can see actually that the 31st of July is centered in 0, where where the nucleus is supposed to be and where we all align our beams to. And the other one is shifted and it's huge. So we did also the comparison, not just only with the production rate, which is a quantitative measurement, but we also check the area under the curve just to understand the percentage of things in excess, and they match. So it's kind of 50-50, I would say, icy grain. So it was big. It was a big outburst. Yeah. And so we were wondering, how can we use water as a reference if water varies, right? And so we have to see how the other molecules varies to understand if actually we can still use water or not. And we actually did use water because because other molecules, some of them, I'm spoiling the results, but it's fine. Some of them were following water and some other did not. So yeah, so if we can go to the mixing ratio plot, I can show you.
There we go, relative to water.
There we go. Yeah, then we compare with other measurements. That's what we have to do, understanding also if other people and other measurement were consistent with ours. And we actually found consistency with the SOHO measurements. The water production rate there was higher, but because the field of view was bigger and there were many other things going on, different instruments. They were only measuring H, so hydrogen, the Lyman alpha, so they might not come in also from water, but from something else. But let's say that we were in the order of magnitude consistent with them too. And so these are our mixing ratios. So in here, things start to get interesting. Indeed. So let's try to understand what this plot is, and then to put them together, the information also with the spatial profile that we just discussed. So this is the ratio of the production rate of each molecule. So starting from methanol, ethane, methane, CO, HCN, ammonia, acetylene, and formaldehyde relative to water. Each molecule has a color, and actually they have the same color across the whole manuscript, also in the spectra. Yes. So that people can always reconnect that, across the paper. And so the round circles are ice shell measurements, and the stars are Keck.
Yep.
Yeah, so basically we report here the mixing ratio relative to water, and then rescaled to a reference value. So they are all, going close to 1, or they're all rescaled so that we can compare them all, basically. And the reference values here are reported in the plot. Like, for example, methanol is 2.61. And below the reference value, we report also the 55 and the 75 percentile of the distribution.
Got it. Okay.
Yes, and these values are updated from a recent manuscript, Lippi et al. 2021, which is Manuela is the second author of this article. Okay. And also from the Lorusso et al. 2016, which is a review paper about taxonomy on comets, basically. And so we take the value from these two papers, which were updated, and we put them together. And I also add a few more measurements in the last 4 years of comets that were published. So we have this reference baseline for all these molecules, and we compare our mixing ratios relative to this baseline. And so interestingly, what we see is that usually what you expect that a comet has that composition, right? So if you measure one molecule, it should be that value relative to water, right? But it was not. And so that means that the nucleus was not very uniform. That's why we say that we are seeing heterogeneous composition in some way. And we're going to go into the details more on this. Like, what we saw was that the mixing ratio for some molecules, like if you look at acetylene, or if you look at ammonia, might even HCN and CO, this molecule here on the right plus the CO, we can say that the mixing ratio is within the percentiles of the distribution. It varies a little bit, but it's pretty much stable. And the variation are within the percentile. It doesn't go out of what is expected to be, right?
Right.
While if you see the percentile, this 25th and 75 for methanol, HCN, ethane and methane, the value changed dramatically. And for methane and ethane, the mixing ratio goes from being depleted in those molecules to be enriched in those molecules. And I've been reprocessing the data many times because I was like, I'm doing something wrong. But it was coming always like that. So that's a very interesting thing, because what we saw is that the mixing ratio are changing dramatically from 3 days, and then for the following observation, they are completely different.
Yep.
But some of them follows water, because why? Because acetylene and HCN and CO, they follow water. They do not change dramatically. And some of them are measured on the same dates of those that changed.
Yes.
So it means that some molecules follow water and some other molecules are not, or it means that maybe this is an indication that the release of the material that we saw in the first state, where we had this excess of icy grains coming from these outbursts or these jets or something, was maybe from a boulder of part of the nucleus or something that was chemically different from the other part.
Heterogeneous, yep.
Right, exactly. And we've been seeing, for example, 67P, the target of the Rosetta mission.
Okay.
It was made of probably two big boulders, right? And 103P, Arclay 2, has this shape where the neck had a composition and was completely different from the other boulder that was not enriched, was depleted in water vapor, but was enriched in CO2 ices and water ices. So you can see this kind of heterogeneous composition in nuclei, right? So we assume that they are not like homogeneous. And so I think this was an interesting evidence that if you put it together, the mixing ratios are varying so much with this shift, which are an indication of something that is released in that direction and sublimate there at that distance. It might be an indication of these grains, which might be nearly pure waterized grains or mixture of those together with some other ices, which are sublimating. And in some way, we can see these differences. So it was super interesting, in my opinion, to see these mixing ratios, because usually you expect them flat, constant, right?
Exactly. Yeah.
So that was a very nice indication. And also when we think about to put in context these studies, right? Because as cometary scientists, why we want to study those objects. And they are interesting because even if they're always called the minor body of the solar system, I think they play a major role, right? In trying to understand, the origin of our solar system. And so trying to understand where these objects form, where these bodies form. And so when you see something like this, I thought about that we might have different location for different boulders or different pre-cometary embryos where each different embryo form a different temperature and went through different processing. So some of them might be form in a very warm region of the protoplanetary disk where CO was in the gas form, and so that or maybe some other boulder or cometary embryos were formed in a very cold region where CO froze, and on grain surfaces, hydrogenation reaction brought to these more complex organics. So both fit this scenario, no?
Yep.
And so why not? We can think about that with our interpretation of these profiles, mixing ratios can be heterogeneous nucleus for this comet.
Yeah.
So cool. Very interesting, I would say.
Very cool.
Yes. And I hope people got fascinated about this. I was
you hooked me.
I was very fascinated about this comet, and really
very cool.
Yeah.
Very cool.
So we hope actually then the next one is gonna be as much as exciting, which is gonna actually happen these days.
Yes.
Yeah, because we have another Christmas comet coming, the Comet Leonard.
Yep.
Yeah, and we have scheduled observation this Monday and Wednesday coming. The comet is brightening up from being 5 magnitude is now around 3. So it's incredible. So we hope that we're gonna see something interesting and compare and reconnect together. That would be interesting. Yeah.
Okay. Sara, I want to thank you so much for walking us through your really lovely AJ article. Thanks.
Oh, my pleasure. Thank you for inviting me. Really, I'm very happy about it.
And you touched on it a little bit there at the end, that you're going to be having some new data come in from a new comet, and so it'll be interesting to see whether you see the same phenomena in 2 different comets. That would be interesting. But are there other aspects one could go after? For example, are there different theoretical models? What is the uncertainty in those theoretical models and how they might impact your interpretation? Is there laboratory astrophysics experiments that could be done to help inform these apparently heterogeneous compositions? And how about those unidentified lines? Would do some things. So just kind of give it a future look on, you know, where we might go over the next couple of years on resolving these mysteries.
Yes, so I can say that, so what I presented here was the molecular mixing ratios, right? But there are many other things that we can investigate. For example, even the ortho to para ratio, which is a topic that has been broadly debated, if it's cosmogonic or not, if it contain and maintain and preserve the information of the spin temperature or not. And so, of course, laboratory experiments on species that can provide ortho para and more measurement and improvement of those, right, can definitely help in understanding more questions that we have, right? Not just the mixing ratio that we've been exploring now, but other questions about cometary science that aren't resolved. And also, for example, with the advent of new instrumentation, we can explore more the D over H, which is another very important cosmogonic parameter that we want to study in comets. As I mentioned earlier, we had this measurement that we're going to publish for this comet, but D over H is a very tough measurement, especially at infrared wavelength, right? So yeah, so also for in the future of the instrumentation, also with the JWST or other instrumentation, we hope we can get information about, more detailed information about Comet. And to say also from the ground-based point of view, instrument like the NeoSpec KEK or IRTF, right, iShell, they will still be competitive and they will provide complementary information to instrumentation like the JWST, right? Because, for example, they will provide more accurate rotational temperature measurement because we can see all these high resolution, we can see all these lines, right? While the JWST will have a lower resolution around 3000, something like that. So complementary, we can get information that the JWST will provide the CO2 measurements, for example, that it's not possible from the ground, but we can then put them together. So yeah, the future, I would say there is so much to do from the molecular point of view, from the lab point of view, you know, from the observation, and there is always a comet coming. So it's something that
I love that optimism. Yes, always a comic thing. Very cool. Very cool. Well, I look forward to seeing a number of these analysis papers in the future on this new stuff. So it's very awesome. And that will do. So thank you once again, Sara.
Thank you so much. Thank you.
And that'll do, everyone. And I hope this made your astronomy day just a little bit better. And we'll see you on the next one. Bye-bye.
Bye, everybody. Thank you for following.